Okay, welcome back. We're talking more about fuzzy logic and its interesting part. We're going to develop today probably the most important application of fuzzy logic, which is to fuzzy inference, which is used for fuzzy control. I think, as I mentioned in the beginning, that fuzzy control or control theory in general is usually taught with a high degree of analyticity. And it works, minimum phase, keep all your poles in the correct half of the plane and things of that sort to assure stability. Um, there's the x dot is equal to ax plus bu. Everybody studies that to death, and that's a lot of work to do, and you got to really be knowledgeable about mathematics in order to do it. With fuzzy logic, the idea is that we would take ways that we control things day to day, and we are able to translate it into machine code. Usually it doesn't work perfectly because, as you see, there's a lot of slop in the application, the idea of fuzzy logic. There's a lot of slop there. So, what you normally have to do is you have to go back and you have to tune things. And it's just like any design. If you have any design, usually your first design doesn't work. So you go back and you twist some knobs and different parameters to make it work a little bit better. And then you twist it again to make it look a little bit better. And pretty soon you're doing okay. So that's what happens with fuzzy logic. You want your fuzzy control system to do something. If it doesn't do it, you can kind of identify it and go back and tune your fuzzy logic. And it's very heuristic. You can actually do the math. I did a couple of papers on using steepest descent in order to improve the performance of fuzzy logic. But then you have to know exactly how you want your system to perform. So we talked about last time of a weird sort of problem, which is concatenating two very dissimilar fuzzy membership groups. Number one was liquids that taste good, and number two, cities which were far from LA. And so we had the good tasting water is 0.0 for swamp water, 0.5 for radish juice, and zero point 0.9 for grape juice. LA, which is something that we've seen before, is 0.5 for Chicago, 0.8 for New York, and zero point 0.9 for London. So how do we talk about the idea of liquids that taste good and cities that are far from LA? Well, it turns out that indeed you can do that. You can do that through an outer product. When you take an outer product, you are, if you will, taking two vectors and making them into a matrix. What we've talked about before is taking two vectors and making them into a scalar, but here we're taking two vectors and we're making them into a matrix. And so here on the left, we have swamp water, radish juice, and grape juice, 0.0, 0.5, 0.9. And then we have LA, Chicago, zero point 0.5, New York, zero point 0.8, and London, zero point 0.9. And so what we want is we want to find liquids that taste good and cities that are close to LA. What is and? And is a minimum. So therefore, we go through and we take the minimum in each case. So we have, for example, grape juice. If we look at the idea of grape juice and New York together, the minimum of that is 0.72 if you use min-max logic. Now, if we were using some product logic, so we're actually doing a product here. If indeed it was min-max logic, this would be a 0.8. So you can see that it's simply taking all of these two vectors, or these two vectors, and doing the minimum of each one in order to get the and right. And again, I'm using the sum product form of ands and ors, where the anding is a product and the summation is a or, but the summation, if you remember, doesn't exceed one. And so we have, let's see, where did I have that? I forget where I had it. But we have to go ahead. Question? Okay, make sure you're muted, if you will. So I'm going to illustrate this idea through the idea of fuzzy resemblance. Let's talk about fuzzy resemblance, fuzzy composition or resemblance. So I don't know if you know who this guy is. Anybody know who this guy is? You got to be an old guy to know who this guy is. He lost a race for president of the United States. That's John Kerry. And you really got to be an old guy to know this guy. Anybody know who this guy is? Wow, that's Stan Laurel. Laurel and Hardy were a great comedic group that they were a pair, and they started out in silent films. And when silent films became talkies, there were a few people that could make the transition from the silent film to the talkie. An exception was Laurel and his partner, Hardy. He was a skinny guy, he was the fat guy. And their videos are hilarious. I invite you to go to YouTube someday and watch one of their videos, Laurel and Hardy. So they made the transition, and not only made the transition, but they thrived. And the reason I put these two guys up there is because they kind of resemble each other, don't they? You know, they have the long chins, they have the creepy smile and the raised eyebrows. And so there is a resemblance there. How do we measure resemblance? Resemblance is a fuzzy sort of idea. So we can assign a number between 0 and 1 of the resemblance between Laurel here, Stan Laurel, and John Kerry. They do have a resemblance. So let's talk about fuzzy resemblance. Here we have on the top, we have a professor, and then we have this turns out to be my son Joshua, and this is me before the operation, and this is Joshua, who's much older right now, but I use these pictures because I wanted to get the resemblance well. And these are the movie stars. This is Matt Damon and this is Tom Cruise. Now, what we're going to do is we're going to look at the resemblance between these people. Is that okay? So let's look at the resemblance between Joshua and Matt Damon. I would say that's a zero point 0.8. I think it's probably pretty close. You agree? Kind of like that. And let's look at the resemblance between Matt Damon and the professor. Not very much, not very much at all. So I would call that a zero point 0.1. Again, these are all heuristic, right? Let's look at Joshua and I was going to say Ted Cruz. No, Tom Cruise. Joshua and Tom Cruise is a zero point 0.2. They don't look at all alike. But if you look at the professor and you look at Tom Cruise, you notice that both are handsome, both have a beard. So I assign this a zero point 0.8. What do you think? Okay, so that's good. Or a zero point 0.9. So I can actually go in and apply my own bias, if you will, and give myself a zero point 0.9. Okay, so we're going to ask the question, given these relationships, how much does Matt Damon resemble uh, Ted Cruz? I can't get that out of my mind. How much does Damon resemble Cruz? Can we, from just this data, figure out how much that Damon resembles Cruz? You get the idea? So let's talk about this. So I maintain that Damon resembles Tom Cruise if Matt Damon resembles Josh and Josh resembles Tom Cruise. That's one of the criteria. So if Matt Damon or if Josh resembles Matt Damon and Josh resembles Ted Cruz, then probably Ted Cruz and Matt Damon kind of look alike, right? Let me say it again because it goes by fast. If Josh resembles Matt Damon and he resembles Tom Cruise, then Tom Cruise probably resembles Matt Damon. You got the idea? Also, it could be the other way around. We've just gone down the resemblance to Josh. Or Matt Damon resembles Tom Cruise if Matt Damon resembles the professor and the professor resembles Tom Cruise. So what does this mean? Well, this tells you to do something. Okay, let's be careful and apply the first one. Matt Damon resembles Josh, and Josh resembles Tom Cruise. That's an and operation. That's a minimum operation. So therefore, we take a slice down the left-hand column, and to get that first measure, we're going to take the minimum of those two, and that's the measure of Matt Damon resembling Josh and Josh resembling Tom Cruise if we use min-max logic. You with me? On the other hand, we can also say that it also is true if Matt Damon resembles the professor and the professor resembles Tom Cruise. So this goes down the right hand column. And so we take the minimum here. So what we've done is we've taken these two statements of Josh resembling Tom Cruise and Matt Damon resembling Josh, and then gone through the second step too. But just mathematically, it's easy to see that this is just a column sort of minimization which happens. And so we have the first part, then we have the second part. And so what are we going to do? We're going to put it together with an or. And that or is a maximum, right? So we're going to take the outcome of this column, the output of this column, and take the maximum. I see it's a little bit off screen here, but it's a 0.2. It's a maximum operation. And so the degree, at least from this analysis, that Tom Cruise resembles Matt Damon is a 0.2. This is inferred from the other resemblances. Isn't that weird? The answer is yes. Here's an alternative view of the same product or the same problem, and that is the idea of an inner product. If you recall the operation of two inner products, recall the operation of the inner product of two different vectors. So part of that matrix is Joshua and the professor with Matt Damon, 0.8 and 0.1. The other part of that matrix can be written as Tom Cruise with Joshua and the professor. Now you'll notice that in order to multiply two vectors, that the vectors have to match each other, at least in one dimension, right? So the vectors have to match each other with Joshua and the professor, Joshua and the professor. And so what we're actually going to do is we're going to take the inner product of this and we obtain the following. We obtain a 0.2. Notice something very interesting, and we're going to see this happening again and again, is the idea that this looks like matrix multiplication, doesn't it? What is the difference? The difference is that instead of multiplication, we use a minimum operation. Instead of addition, we use a maximum operation. So think of multiplying these two just like a regular vector, except where you multiply, use a min, and where you add, you use a max. And this is what happens to fuzzy logic sort of concatenation, if you will. The min is replaced by the min replaces the multiplication. The max replaces the addition. And you can see that's exactly what we have here. We have the minimum of 0.8, 0.2, and 0.1, 0.9, and then the maximum of that, which is 0.2. So again, it's just like regular multiplication, an outer product of two different vectors, except that min replaces multiplication and max replaces addition. We can talk about this so-called composition operator, and that's what I've used here. It's covered up a little bit, but it's a little circle. It's the same as conventional matrix multiplication, except the max replaces the addition and min replaces multiplication. Now, again, this can be applied to some product logic. We'll also see other techniques to perform mins and maxes, but that's what we're doing here. So with this in mind, let's show exactly what happens. Yep. So that's what happens. Now, let's look at a longer example. So here's a more interesting, longer example. In the upper left, we have a strange-looking lady. Anybody recognize where this is from? You do? Okay. Where's it from?
Planet of the Apes.
Planet of the Apes. That's right. In fact, it's the first Planet of the Apes. And we want to look at her resemblance to all of these people here. Anybody know the guy on the left? I used to know, but I forgot. There's Hitler, and then there's a funny looking guy. There's a guy that has a long beard with a mustache and a little thing below his lip. Anybody know who that is? This shows you that fame is very fleeting. He used to be a a great rock and roll sort of performer named Frank Zappa, and he's in the Rock and Roll Hall of Fame. And then to his right is a guy that just retired. He got kicked off of the Sirius FM because nobody was listening to him anymore. That's Howard Stern. He was kind of a shock jock, kind of a vile person in life. And then to the right of that is a dog. So we're going to look at the fuzzy resemblance between this monkey lady, this ape lady, and um, we're going to look at how she resembles these other people. Now, again, to do this, it's very heuristic, isn't it? So this is what we're going to do. I'm going to say that the guy on the left is a 0. She resembles Hitler at about a zero point 0.1. The I don't know, that guy third from the left. I don't know if that's a girl or a boy. I think it's a man. The guy third from the left is a zero point 0.3. Frank Zappa is a zero point 0.5. Howard Stern is a zero point 0.8. And the dog, I was going to give it a 0.0, but I give it a zero point 0.1. You notice these are just like judges judging a high dive, the quality of a high dive. Everything is heuristic. Everything is on a scale of 0 to 1. Resemblance can probably be quantified, but I don't know if it can be objectively quantified as well as we do it as human beings. I don't know. So let's take a look now at another person, and everybody knows who that is. That's Michael Jackson. And we're going to look at his resemblance to each of these people. And in the end, our job is to figure out the degree that Michael Jackson looks like the ape lady. There is some resemblance, right? I mean, they both have kind of the hair, they both have lips, very nice chins. So we'll see. Anyway, this is what I gave for this. The fuzzy resemblance. I gave 0.0. Hitler was 0.0, 0.4 for the guy with the curly hair, 0.6 for Frank Zappa, 0.7 for Stern, Howard Stern, and zero point 0.0 for the dog. And so, how can we then determine the resemblance of the ape lady with Michael Jackson? Well, we would take the inner product of these two vectors, except we would use minimum for multiplication and we would use maximum for addition. So if we take that result or that approach and use the min and max, then we're going to get a result. So if we take the inner product, multiplying two vectors together to get a scalar, with again min as a multiplication and max as a addition. So we use the composition idea. We get that the resemblance of the monkey lady to Michael Jackson is a zero point 0.7. And I would say if I just saw the monkey lady and Michael Jackson, these pictures together, I would say it's a zero point 0.7. That's probably a decent relationship. So what is the weak link here? The weak link is Howard Stern, because you notice his resemblance to the monkey lady and his resemblance to Michael Jackson are both very, very strong. So he's the guy that brings it through and brings the resemblance to the final conclusion that, yep, Michael Jackson does resemble the fuzzy lady on a scale of 1 to 10. He resembles it on a scale of 7. So therefore, we have this idea which is emerging of matrices in fuzzy logic. And we can indeed have another example. Here's another example. This is Michael Jackson. Anybody recognize the guy in the middle at the top? He used to have a kids' TV show. He did a couple movies. That's the guy that played Pee Wee Herman. Remember Pee Wee Herman? Anybody know Pee Wee Herman? I think that's a mugshot. He got arrested for some things. So we got the monkey lady. Then we have Frank Zappa, the curly-headed guy. And I just entered a bunch of membership functions here for them. And this is pairwise. This is Michael Jackson and Frank Zappa's a zero point 0.6 to the upper left and 0.7, 0.4. And you can see the elements in the matrix in terms of the resemblance. Then we can do a composition with the Michael Jackson, Paul Rubin, who played the Pee Wee Herman, and then the monkey lady. And then on the right here, we get Howard Stern and the dog. Notice that the three vectors on the top here, or the three elements of the vector, have to be named exactly the same as these three elements in order to multiply the two together. So we're going to multiply the two together and we get a larger composite. We just don't get one number. We get the relationship, the resemblance between Frank Zappa, the curly headed guy, and Howard Stern, the dog. And that turns out to be 0.6, 0.4, 0.5, 0.2. Again, multiplication is minimum. Addition is replaced by maximum. So this is our final result, and it kind of makes sense that we have Howard Stern there looking like Frank Zappa, but not too much the dog, maybe a little bit of the dog. They both got a lot of hair on them. Howard Stern and the fuzzy-headed guy is a 0.5, but the dog and the fuzzy-headed guy are much different. And they're a 0.1. They don't resemble each other. So hopefully you can see this is kind of interesting. And this sort of multiplication is the foundation for the fuzzy inference that we're going to study next. So let's talk about the fuzzy inference that we're going to study next. Here's what we're going to do. We're going to have a control problem. And the control problem always has its input. For example, you might have as an input the position, the velocity, and the acceleration of an object. And what you want to have is some sort of goal, some sort of consequent. So you have the antecedent, which is the input. You have the consequent, which is the output. So the antecedent is going to be a number of different variables describing what happens when you when you actuate this. And then the consequent, you want a certain consequent if those antecedents are one thing, and you want a different consequent if they're something else. So these are the rules, and yes, these are actually words that you can look up, and I think they're in the dictionary. We're going to do fuzzification. We're going to take the crisp input because we measure crisp things in terms of definitive measures, like we measure distance in terms of feet or miles. We measure velocity in miles per hour. We measure acceleration in miles per hour squared. And so we have specific numbers here describing, for example, the operation of our plant, of what we're trying to control. So we're actually going to make this fuzzy, and then we are going to apply rules. And these rules are the ones that are going to be set up by heuristics. Just like in a lot of fuzzy logic, it's all heuristics. We're dealing with fuzzy concepts here. Then from the fuzzification and the rules that we generate on the side, we go through the idea of defuzzification and generate the consequent. The rules will give us a fuzzy measure, which we have to defuzzify. Yes, that's also a word, defuzzify. This is one of the reasons that fuzzy logic was not accepted. I told you the example at Boeing, for example, where they didn't like the word fuzzy logic. Well, you'd think they would like fuzzification and defuzzification? I don't think so. So a lot of people came out and started calling fuzzy sets, they called them soft sets instead of fuzzy. And soft has a better political interpretation than does fuzzy. So sometimes you might see soft logic as applied to, soft logic defining fuzzy logic, but it's the same thing. And then you'll get a crisp output. You have to have a number, you have to have a specific action which determines your consequent. Now, if you look at these initially, and it's the first time you've seen them, you got to go, geez, I don't understand what's going on here. But you shouldn't. But that's the job now. My job is to explain it to you. So let's talk about admission to graduate school. You all have been admitted to graduate school. So we're going to make an expert system determining whether you get into graduate school as a function of your GRE and of your GPA, your grade point average, and your GRE examination, which used to be required every place, but now we're not requiring it anymore. They got politically correct. They kind of ruined their reputation, and they tried to climb back, and people are really not doing this anymore. If you recall, Bob Bittmead in the beginning said that he didn't like the idea of the claptrap of fuzzy logic and neural networks being a new age solution to some of these things. The person who countered was the person that came up with fuzzy inference, which was Mamdani, and this is him on the right. He just passed away, and he was very interesting guy. He responded to Bitmead by saying that you are so entrenched in your ideology, in your cult of analyticity, in your cult of Laplace transforms and minimum phase and all of this other stuff, that you don't see that there are other solutions in the world. You have dug yourself a trough so deep that you can't see out of the edges. So take a look out of the edges and see it works. Now, anytime there's a controversy about adoption of a new technology, this includes AI, for example, how is it decided? It's decided by its reduction to practice. Do people actually use it to their advantage in places such as business, the military, government, or other places? And usually it has to be an order of magnitude better or easier or cheaper in order to be applied. And that was indeed what happened with some of these fuzzy logic. Now, fuzzy logic is applicable primarily to simple systems, and we'll get into simple systems, but a lot of things are simple systems. You talk about the y dots equal to ax plus bu. We talk about that. Usually the inputs are, you know, finite. You have maybe four or five, and you can handle that with fuzzy logic, but it's easiest to describe it in terms of two. So we need to evaluate a student application to graduate school based on their undergraduate GPA and GRE scores. One of the challenges historically with this, as one who sat in a lot of admission committees, is that the GPA is a pretty noisy measure. If you go to some schools, it's easy to get a GPA, and with grade inflation, everybody wants to celebrate. Yeah, everybody wants to celebrate the fact that they got good grades and are looking good, and everybody wants to do retention. This is a big thing in universities. Our president just put out this message that she's so happy that we have like a 70% graduation rate of people that have applied and started at Baylor. And I think that that's something terrible because what you're doing is you're trying to make the numbers bigger without paying very much attention to the quality. When I first started into graduate school, I went to Rose-Hulman, and the dean there was called Dean Munch. And one of the big buildings at Rose-Hulman now is called Munch Hall. Really nice guy, really smart guy. He got up at freshman orientation and he said, look to your left, look to your right. He says, one of these people are not going to be here next year. They used to make engineering undergraduates so difficult that they wanted to flunk out people on purpose. Well, I don't think they wanted to flunk them out on purpose. Everybody was rooting for everybody, but they knew that everybody didn't have what it took to be an engineer. Well, now that's much different. Now, if you go to a freshman orientation, they say, look to your right and look to your left. We're going to do all that we can to keep these people here. So things have really changed. And why is the reason that they've changed? Well, I think it's changed because of money, right? They want to keep up their tuition and all of the good incomes that universities get. What is it that Harvard has an endowment like $12 billion or something? Wow, that's pretty cool. Okay, so this is our expert system to evaluate the GPA and the GRE. And this is an expert system in the sense that you're applying domain expertise in order to determine whether a student should be admitted. And here's what we're going to do. For simplicity, we're going to have three categories for each score. For the GPA, we're going to have an idea for the high GPA, a medium GPA, and a low GPA. Same thing for the GRE. We're going to have a high GRE, a medium GRE, and a low GRE. And we're going to assign fuzzy membership functions based on the actual numbers associated with the numerical results of each one. Let's assume that the decision should be excellent, very good, good, fair, or poor. In other words, the GRE and the GPA are the antecedents to the problem, to the expert systems. The consequent is the final ranking. So the antecedent, the input is the GRE and the GPA. The antecedent or the output is the final ranking of excellent, very good, good, fair, or poor. And these, again, are all fuzzy sort of linguistic variables. An expert will associate the decisions to the GPA and GRE scores. So when you have somebody start an expert system, it's very good if they have a domain expertise in what the heck is going on. So that's what we're assuming here. This is going back to Minsky. You remember Minsky used to battle um, people such as Rosenblatt and Woodrow, and because he said expert systems were better than neural networks or connectionists. Well, this is an example of a expert system initially is set up, but you can apply AI to it and tuning to it to automatically tune the fuzzy membership functions and other things to get a result that you think is best. So it's kind of hybrid. We see the same thing today with large language models. I just wrote a column illustrating how large language models have a lot of people behind the scenes doing crafting things. We discussed this in the first part of the course. Remember the idea of the lady with no teeth and no elephants? Well, that was in 2024. Now, if you ask it for no elephants, it'll give you no elephants. The other example that we used a long time ago was this. John's mother had three kids, Snap, Crackle, and usually the response was Pop because of the Rice Krispies character, but no, it was Snap, Crackle, and John because the whole thing started out as John's mother had three things. So there are people in the background. So even today, my point is even today we have AI, but we have people behind the scenes, and we have people behind the scenes doing all of these tunings to the artificial intelligence based on user input, based on what they notice is wrong, based on the way that they want to augment their large language model to do things like extra mathematics or really detailed images. So we have a lot of people just working behind the scenes. These are experts which are applying to large language models. So large language models, the AI came first, and then the fine tuning, the expert systems, the people with domain expertise, making sure that these large language models work. For the fuzzy, it turns out that initially we're going to go with the domain expertise. Then we can use the AI in order to tune things. So let's talk about this. Here's a table. This is a table, and on the top here is GRE, and GPA is on the vertical axis. And we have the three scores, high, medium, and low. So we're going to put up this table, and we're going to make it totally by our intuition and our expertise. If the GRE is high and the GPA is low, then we should probably form in the upper left part of the matrix an E for excellent. So if the GRE is high and the GPA is high, they're probably going to be an excellent student. If the GRE is medium and the GPA is high, yeah, they'll probably be a good student. If the GPA is high and the GRE is low, that means they might be a fair student. In other words, these are either people that have come from a school with great inflation or they know how to take tests. I'm sorry. I just saw Mr. Patel doing exercises on the video. That was interesting. I think, Mr. Patel, that probably detracts from my lecture. So, but no, go ahead. If anybody wants to exercise, I think I'll block it out when I make the final video. So don't have offense. Okay. So let's get back to the I'm going to put that in the final cut, though, Mr. Patel, so you'll be able to see what everybody else saw. Okay, good, good. It's very, very impressive. Okay, so GRE GPA. Okay, so if the GPA is high, median, low, if it's median, and then you can fill in the rest of the matrix. If it's the GPA is median, but the GRE is high, I kind of like that because that means the kid has a lot of inherent talent. However, it might have meant also that the student was lazy because they didn't get a high GPA. So that degrades it from excellent. And then we have good here for medium GRE and medium GPA. And then if you have a low GRE and a medium GPA, well, you're probably a bad student. Uh, Whoop. And then for a high and then a high GRE, and you can read the matrix here, and you can see that for the medium and low, if either one of them, if anything is low, if you get a low GPA or a low GRE, you're going to be bad. You're going to get a B in the matrix here. So does that make sense for an expert system based totally on fuzzy linguistic variables? So we have these. So now we have to take the idea of the input, the antecedent, and we have to perform a fuzzification on it. A fuzzifier converts a crisp set into a vector of fuzzy membership values. So we notice that for the GRE, we get a number like 720. For the GPA, we get a number like a 3.6. We're going to take that, we're going to make it into a vector, and we're going to make it into a fuzzy vector. So we're going to associate a number of numbers with each one of the crisp consequence that come out of, I'm sorry, the crisp antecedents that come out as the input for our expert system. And here's what we're going to do. This is going to be the membership function. It has to design, it has to reflect the designer's knowledge, and it provides smooth transitions between fuzzy sets. And that's a reason we like to use like triangles as opposed to rectangles, if you will, because as one rectangle in the fuzzy set diminishes, the other one gets bigger. You'll see what I mean in a minute here. And they should be simple to calculate. It does turn out that we could use Gaussian membership functions, but it turns out that the triangle is probably the easiest to do because it only has a few degrees of freedom associated with it. And you don't have to do a lot of programming to do it. Typical shapes of the membership function are Gaussian. Again, Gaussian is more difficult to compute because it has a an e to the something, trapezoidal and triangular. So here's what we're going to do. This is going to be the membership function for the GRE. Now I'm assuming that the GRE, the combined GRE, has a total score of I forget what the maximum is. Let's say it's 1800. And so we're going to divide this into low, medium, and high. This is totally done on the heuristics. So we have the low here, and then we have the medium, and then we have the high. So we assign three membership functions, one for each of the antecedents. And so we are taking then a crisp input, the crisp GRE, and we are assigning to it three numbers. We're assigning to it the membership function in the low, the membership function in the medium, and the membership function in the high. So we're taking a single scalar number and we're making it into a vector. Now, should I have used three? I don't know. Let's give it a try and see if it works. Maybe as I tune it and redesign it, maybe I want to use four. Maybe I'm using too many. Maybe I want to prune back a little bit. That's going to come out in the performance. But this is going to be my initial take is three different levels, low, medium, and high for the GRE. And we're going to do something similar for the GPA. And so assuming that the GPA has a maximum of 4.0, I would say that anything below a 3.0 would probably be low. From a 2.2 to a 3.8, that would be medium. And then high would be, you can see it's a gradual, it gets bigger and bigger and bigger and bigger. And you get closer to high as your GPA increases. And so these are the fuzzy membership functions that we're having for the GPA. Does that make sense? And again, these are heuristic. These are what we're going to try. And so again, we're going to take a specific GPA, say a GPA of 3, and we're going to make it into a vector. If it's a GPA of 3, then what is the low? The low is 0. What is the medium? It's a 1. What is the high? It's a 0. If we put it right here at the 3.0. So those are the fuzzification of the inputs to the fuzzy system. And this is referred to as fuzzification because we're actually taking a scalar and we're making it into, if you will, a vector. And here's the fuzzy membership of the consequent. Now, with the consequent, we're not going to have a specific number, but we are going to are going to rate it between a 0 and a 100, if you will. And you'll see where this number comes from, this x-axis here. It isn't apparent looking at it initially, but we do have some sort of final ranking of bad, fair, good, and very good. And over here, off scale, is the excellent. And this will tell us the degree to which we would like to have this person be admitted to graduate school based only on the GRE and the GPA. So the first thing we have to do is we have to take the crisp antecedents, because every student coming in is going to have a GRE and a GPA, and we have to assign it some value of numbers. We have to assign it, we are given numbers. We have to fuzzify that into the three numbers. For example, suppose that the GRE is 900. If the GRE is 900, let's look back here. If the GRE is 900, it's about halfway between it's a little bit down here. Can you see my cursor? Okay, you can see my cursor. So it's down here. So the low membership function, if it's 900, the low is going to be, I don't know, 0.4. I'm sorry, the median is going to be 0.4. The low is going to be about 0.6, and the high is going to be 0. Since at 900, it doesn't even intersect the high membership function, right? For the high membership function, the idea is that it's a total 0 here. Okay. Similarly for the GPA, if the GPA is a 3.6, you can see that the GPA is 3.6. So the student that we have in has a GRE of 900 and a GPA of 3.6. So we're going to go to the 3.6. We're going to go up here. This is the GPA. 3.6 is about right here. And you can see that it doesn't have a value for low at all. It has a value of about a third for medium, and it has a value of about 2/3 for high. So the vector is going to be 0, 2/3, high. And so that's the way that we take this single number, we make it into three numbers by looking at the individual components here. And this is what I have. This is what I just showed you. If the GRE is about 900, the three vectors are low is a 0.8, medium is about a 0.2, high is a 0. And if the GPA is what? GPA is 3.6, then that fuzzifies. We're fuzzifying here. Remember I talked about fuzzification? We're fuzzifying here into a 0, a 0.6, and a 0.4. So these are the fuzzy membership functions for the antecedents, the input to our fuzzy logic. So here we have, these are our activated rules, and here's what we do. Now, for the low, medium, and high, we're actually able to put numbers in. For the GRE, our fuzzification result was 0, 0.2, and 0.8. That was the reason, that was the fuzzification for the GRE. We took that GRE and we made it into three numbers corresponding to how much it's set in each of the three sets. Similarly, with the GPA, we got the number 0.4, 0.6, and 0 for bad. And the student is good if what? If these are true, each one of these has a certain evaluation concerned with it. So if we look at this and we look at the minimum, because we want to have a good student, it has to have a good GRE and a good GPA. So what happened? Well, this is a good GRE and a great GPA, and that's going to be a 0.2. So if we take the minimum of 0.2 and 0.4, we get 0.2 using min-max logic. In a similar fashion, using 0.4 and 0.8, we get a 0.4, which is the minimum of those two. So in each case, we take the minimum of the results. We take the minimum of 0.2 and 0.6, and that's a 0.2, and then we have a 0.6. So here's one way to figure out the consequent. How is the student good? Well, he's good if this is true, or this is true, or this is true. Whoop. It's true if this is true, or 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 this is true. What is that or? That's a maximum. So if we were to use the strict maximum, and by the way, that's not the way that it's typically done, but if we were to use a strict maximum, we would come up with that on a scale of 0 to 1 that this student was a 0.6 in terms of excellence. So again, we got the entrance in the matrix using the minimum operation. We got the composition by taking the maximum because a student is good if any one of these is good. And we got a 0.6 as a result. So again, applying the min-max sort of idea of Zada. Again, it doesn't have to be the min-max. It could be the sum product. It could be something else. And you can look at the students and you can look at their ratings and you can say, this is not right. I need to go back and tweak something. And so that's typically what you'll do. So here's a better way, instead of doing the maximum, of doing the weighted consequent membership function. And here is the idea. We have the membership function of bad, fair, good, and very good. And what does that mean? Notice that I have multiplied or scaled these membership functions by something. What have I scaled them by? I have scaled them by these results here. Okay. So they are scaled by the different outcomes of the defuzzification. Now, these are again the membership functions multiplied by the corresponding consequent numbers. And what we want to do is the following. This is what is typically done instead of taking the max, is taking the center of mass of this. In other words, we're going to take the results here. These are the membership functions weighted by how good they were. And we're going to add them up and we're going to take the average or the center of mass of them. And that's going to be the result. It's just like taking the average of a probability density function, right? The average of a probability density function, if you took the density function and you cut it out of wood, there would be a certain point where it would balance. And that's what we're doing here. We're taking the point where it balances. And that point where it balances, which is the mean, if you will, of the summation of all of these things, is what the result's going to be. So if we use this technique, we find out that it's a 70. So this is kind of a fair student. So this is the max method, which I talked about. I've already talked about the max method. And the max method is also known as the mode method because we have a distribution here. And the mode, remember, is where the probability density function achieves its highest value. And so we're using the mode here. And the mode is a measure of central tendency. If you remember probability, there's three ways where we can determine if we're given a probability density function, what kind of something in the middle corresponds to. We can use the median, the mean, and the max. Remember, the median, the mean, and the max. All three of them can be different. There are certain cases where all three are different. There are some cases where all three are the same. But the mean, the mode, and the maximum all try to measure where this balance occurs at in the fuzzy membership functions. If we just use the max, we're using a mode for sort of defuzzification. If we're using the center of mass sort of idea, then we're using a mean sort of distribution. We could also use a median sort of distribution. We could kind of choose the point where 50% of the area was on one side and 50% of the area was on the other side. So there is no right way to do this, but I think that the average is the one that works the most and most effectively. Okay, so I think that's it. Thank you.